Here's a short extra example on higher order derivative on page 63. So in this example, we have this position function, but this position function x of t is given as a product, but I don't want to use a product rule unless I absolutely need to. So what I will do is I will actually do some algebra, like I will FOIL it out, distribute it out so that it's in a standard form, okay? So look at my algebra work over here for me. So x of t, I write this as t times t minus 4 squared, which is t minus 4 times t minus 4, right? I'll FOIL. I'll FOIL first. That's going to be t squared minus 4t minus another 4t and 4 times 4, but that's going to be negative times negative, so I'll write plus 16. This is t times t squared minus, combine the like terms to get 8t plus 16. Lastly, I will distribute this t and get t cubed minus 8t squared plus 16t. So here's our brand new x of t, all multiplied out. And why would I do that? I don't want to use product rule. I will just take the derivative of this, and that will be the velocity function. So let's take the derivative of the line above, and that's going to be the velocity function. The first term will be 3t squared, the next term will be 6t, and lastly plus 16. So just wanted to show you that you do not have to work with product rule and chain rule if you want to just do some algebra manipulation to rewrite your function in a standard form, okay? Now, the value of t when particle is instantaneously at rest. So they're asking for when the rate of change of this particle is 0, okay? At rest, it's not moving, the speed is 0. So what you will do is set this velocity function equal to 0, okay? So let's do that. So we say v of t equals 0. And v of t, we found that above 3t squared minus 6t plus 16. We're trying to see if that's equal to 0. Ugh, I don't think this is factorable. I try to factor 3 out, but I don't think it's going to work. So let's just jump right into the quadratic formula, where a is 3, b is negative 6, and c is 16. So using the quadratic formula, we'll be able to find the t value. And it goes like that, right? Negative b plus or minus b squared minus 4ac all over 2a. So let's plug in everything, okay? The top of the fraction, we will have negative 6, which is positive 6. And if you square negative 6 inside the square root, you will get positive 36 minus 4 times 3 times 16 all over 2 times a value of 3. All right, we're going to get two answers, right? One positive and one negative. You use this symbol, or maybe both of them are positive or negative, but let me get a scientific calculator out. Okay, so first I'm typing in the plus version. So I will do a fraction bar, 6 plus square root of 36 minus 4 times 3 times 16 all over 2 times 3. There's an undefined. What must be going on? Let me double check my work. Maybe there's no solution to this, okay? But it's also possible that I made a mistake on my quadratic formula, so I'm gonna double check. I think the discriminant is coming out to be negative, the way I said it. Okay, so let's see. The derivative, is that correct? Yep. A, B, C, are those correct? Yep. So how about my formula? Negative b squared is 36 minus 4 times a times c. You know, I think what the problem is that c is so big. Look how big the c value is. It was 16. So when you did 4 times 16 times 3, that quantity was way bigger than 36. So when you do small number minus big number, the subtraction came out to be negative. And when the discriminant is negative, we're taking a square root of a negative number. That's not real. That's imaginary. So we're not going to say this particle is instantaneously at rate at an imaginary point in time. So what we're going to say is that since this had no solution, okay, no solution, this particle is never at rest. It's a crazy little particle constantly moving around. This one never stops, okay? Because when you solve this quadratic formula, the t was undefined, okay? So this particle is moving, a crazy little one, but the velocity is never zero, okay? All right, how about acceleration after 4 seconds? Well, to find the acceleration, we will need to find the derivative of the velocity function, how fast the speed is changing. So, acceleration function is the derivative of the velocity function, which is the second derivative of the original function we found. So let me go grab that velocity function real quick. I'll put this one right here. Ooh. And we're going to try to take the derivative of this function, okay? All right, so what's the acceleration function? That will be 6t minus 6. So they're asking us what is the acceleration after 4 seconds. So you plug in 4. 6 times 4 minus 6. That will be 24 minus 6. So what's that going to be? 18. What's the unit going to be? What was the unit of distance? They never said it. So I'm going to just say 4 unit per. Oh, actually, they said it. It was meters at time seconds. So here's the unit for this. Meters per second squared. So that's going to be the acceleration after 4 seconds. It was an interesting problem. I love that part B, because when we got that the velocity is never equal to 0, we can conclude that this particle is never at rest. It's constantly moving.